Hi, it's Mr. T here. Welcome to the second video that goes over the organic chemistry course at level 3 NCEA. In this video I want to talk about alkenes and alkynes. I want to look at how we name them, some geometric isomers or stereoisomers, and also some of the properties of them. So let's start with naming alkenes. So alkenes have this functional group. You'll see a double bond somewhere in the molecule, and if it has that double bond between a carbon and a carbon, we can call it an alkene. If it has this double bond, there is the potential that we could react this with something. We could add more to it by undergoing an addition reaction. Because it can have more added to it, or more bonds, more atoms added to it, it is said to be unsaturated. So here's an example of a molecule. So let's see if we can name it. So remember the steps we do when we're naming. First thing is we look to see what is the general group of compounds it is. In this case we can see it has a double bond, so it's going to be an alkene. Well, now an alkene has the end part of its name ene. We have this longest chain going through there. There are 5 in the longest chain. So we know that the name is going to have pentene as part of its name. Now once we've drawn the longest chain, we want to number it. We want to number it in such a way as this substituent group, I've wrongly called it a functional group here, but this group coming off, okay, is less important than the double bond. The double bond is more important than just a methyl or an ethyl group. So we're going to number it so the double bond has the smallest possible number. And remember, when we do number it, it's given 2 numbers, but it's only the smallest one that counts. So now when we name this, we can call it 4-methyl pent-2-ene. I've actually put a trans in front of here because this has geometric isomers, because and the geometric arrangement is trans. We'll talk about that in the next slide. So stereoisomers or geometric isomers. So here are 2 stereoisomers. Now stereoisomers come about because when we have a double bond between 2 carbons, a carbon can't do what it usually can naturally do along its bond. So between this carbon and this group of hydrogens, or this group at the bottom, they are allowed to swivel around. So they're not held in a fixed position. When we put a double bond in, these groups on either side of this carbon are no longer allowed to change places willy-nilly, right? They're not allowed to change their places. They're stuck in their position. Because these 2 are stuck on the same side, then this is called cis-butene. This is a cis isomer. Because these 2 are stuck on a different side, it's called a trans-butene. So butene here has 2 geometric isomers. So the carbons are all in a line, but because of the double bond, this line is stuck kind of in a C or a curve, and this is just in a straight line. Now, this can be really important to the physical properties of these molecules. Just one other thing to notice here. I haven't put down that this is but-2-ene because you might recognize that the only way that I can have a cis molecule here is if this has a double bond and if it has 2 different groups coming off either side, which this does, but this can only happen in the type of but-2-ene. Sorry, there is no other butene that can do this. A but-1-ene would not have different atoms on the first carbon. There would be 2 hydrogens. So because we can't have a geometric isomer for but-1-ene, and we can only have a geometric isomer for but-2-ene, I don't have to put the 2 in here because cis-butene can only occur on but-2-ene. It's kind of pedantic or picky. If you put the 2 in, you won't get it wrong when you name them. Anyway, just reiterating here, you need to have a double bond and you need to have 2 different groups off either side to have geometric isomers. Let's have a look at another geometric isomer that has chlorines attached to it. So this is a cis version of the geometric isomer, and the geometric isomer here is 1,2-dichloroethene. And it's cis 1,2-dichloroethene. Notice that these chlorine atoms have been drawn with a delta negative here. They have a slightly negative charge because they are more electronegative than the carbon they're attached to. This produces what's called dipole moments, a negative dipole moment and a positive dipole moment that in turn produces a polar bond. Now what we can do is we can say the center of these two negative dipole moments is in between the center of the two chlorine atoms, which is about here. We can say the center of the positive dipole moments is right here in the center between the carbons. Therefore, overall, the positive and the negative centers are in different places, and this molecule is polar. So this is a polar molecule. If we look at its other geometric isomer, the trans one, the center of the highly electronegative chlorines, their dipole moments, their negative dipole moments, is actually in the center of the molecule here. And the center of the positive is in the center as well. So there are no longer two different poles because their poles are at the same place. Their positive and negative are at the same place. This is said to be non-polar. Now, because this is polar, this molecule will form permanent dipole attractions with other molecules. So this, if we had lots of these molecules together, they would have their temporary dipole interactions, that is due to the size of their molar mass or the size of their electron cloud, plus they would also have permanent dipole attractions. The one on the right would still have the same size temporary attractions because it's exactly the same size as the one on the left. It's the same molar mass and it has the same size electron cloud. However, it does not have permanent dipole attractions. Therefore, this one has the similar strength temporary dipole attractions plus permanent. So overall, it has stronger intermolecular attractions between the molecules. If it has stronger intermolecular attractions, it will take more energy to break the bonds. Say when we turn it from a solid to a liquid or a liquid to a solid, and therefore it will have a higher boiling point or a higher melting point. Another thing to note, because this has a polar end to it, this slightly negative side or the slightly positive side, they can form attractions to water molecules. And these attractions that they form, well, the chlorine here may be able to form some hydrogen bonding, but they form attractions with the water molecules. These attractions with the water molecules could be strong enough to overcome or to disrupt the hydrogen bonding that's happening, and therefore it may be able to dissolve. So it depends on the specific molecule, the size of it, and how strong this polar bond, this polar molecule, how polar the molecule is. But it will definitely affect things like its ability to dissolve in polar solvents and the melting and boiling points. So we can identify alkenes and alkynes. Alkynes are molecules that have triple bonds. And we can identify them by adding something called bromine water or something called permanganate. Bromine water relies on the ability of alkenes or alkynes, we could have one with a triple bond here, being able to have these halogens add to them. That is, one of these bonds breaks and it forms an attraction with the halogens, a bond with the halogens here. Now, because this bromine is dissolved in water, we say aqueous here, and it's orange for a start, when it has been added to the new molecule that is colorless, when the reaction happens, the orange color will disappear and it will go colorless. And we will notice that. Now, this happens quickly with alkenes, and if we notice a color change happening quickly, it means we have a double bond present or we have a triple bond present. You can also add permanganate. If you add permanganate to this, it will oxidize and produce something called a diol, but we'll look at this later, and it will go brown, and it will go from purple to brown, and you will notice that. If the permanganate is acidified, it will go from purple to colorless, and we'll look at, but apart from that, usually we just use bromine water and we shake it. So I just introduced alkynes. So the last slide in this video, we'll just quickly go over how we name these. We name them in the same way that we named alkenes, apart from we're now looking for this group here, a triple bond. So here we put the longest chain, we work out what it is, it's pent. Okay, there is a triple bond here coming off number 2, so this is going to be pent 2 ine. Okay, so alkynes have the suffix ine at the end. We put the 2 to represent where that is located in the molecule. Let's have a look at another one. So this one here, notice that because the triple bond is on the right, we start numbering from the right here to give it the smallest possible number. I also have this methyl group sitting here, so this is now going to be 3-methyl. Oh, I've got a bromine there as well. You know what? I think I forgot that one. Can you see what the name for this would be? This one would actually be 1-bromo 3-methyl but 1-ine. I'll see if I can cover up that mistake once I've uploaded the video. Thanks for listening. Look out for the next one. Well, I'm going to talk about how to name haloalkanes, alkanols, and amines.